Okay, we're going to start in Chapter 6 today, and just keep in mind, guys, that if you want to see that last test, set up an appointment. I'll be glad to go over it with you, okay? If you want to see what you're missing or where you've gone wrong, I'll be happy to. You can do it virtually if you want to. You just have to kind of set up an appointment with me. And now we're going to work in this Chapter 6 worksheet, work through it, and I hope I have made it so that it's not too long today. But basically what Chapter 6 is all about is calculating probabilities based on the standard normal curve. And what we're going to be doing today is talking about, and hopefully you've watched the video so you know a bunch of this already. And somebody pointed out there was an error in one of the videos in Chapter 6, I think it was page 10. So if you hit one place where I forget to divide by the standard deviation, it's my mistake, okay? Don't let that confuse you. I'm trying to go back and fix that, but you've probably gotten to that already. So anyway, with Chapter 6, we only have a couple of formulas we have to look at. We have a standard score, which is a z-score, where we calculate it. If we have the data value that we're interested in, and we have the mean and the standard deviation of the population, and that's all Chapter 6 is about, is population data, okay? We changed that in Chapter 7, so get this under your belt, and then in Chapter 7 we go to two other types of problems. But if you have those three things, you can always calculate something called the z-score. And the z-score represents areas under the curve to the left of whatever z is. And there's your table that you've got in your guided notes book. And the area to the left represents the probability, okay? Now, so if we want probability of something, and we have data values or we have standard deviations from the mean, we can calculate it using z-scores, because what z-scores are is standard deviations from the mean, okay? So that's why in the videos I drew a lot of graphs, and in these problems you're going to want to draw and label your graphs. So I've put, for your worksheet, I've got these standard normal curves here. You'll notice that they are symmetrical. They are perfectly centered around the mean. The mean is the dead center of every standard normal curve, and that's why the z-table works so neatly. Somebody has gone and calculated all of these areas for all of these different standard deviations from the mean. Now for the z-table, for this z-score, you'll notice that this table has a negative side and it has a positive side. You'll also notice something else about it. The z's that are negative are always going to be on the left side, the left half of the curve, right? Their area, z-table only gives us area to the left, even if you're on the right side. Give you area. Keep that straight in your head, because in the next section, we're going to hit the t-table, which only gives us area to the right. I mean, could they have made it any more confusing, right? But this one's area to the left, area to the left. So sometimes they ask us a question that we need to answer area to the right. Well, we have to figure out how to calculate that, given the area to the left, okay? So that's what we have to keep in mind. Now, negative z-scores, always going to be on the left side. Think of this like a number line, right? Negative to the left, positive to the right. In the center, what's in the center? 0. Got it? Because the mean of the standard normal curve, standard normal table, the center is always 0. Because it is 0 standard deviations from the mean. The mean's in the middle. Does that make sense to you? Okay, so as we deviate from the mean, as we get further to the left, we get negative z-scores, negative standard deviations. As we get further to the right, we get positive standard deviations from the mean. But the area from a z-score is always going to be the area to the left. So if I have a negative z-score, the biggest that the area can ever be is going to be 0.5. Because the biggest it can be, guys, is down here, and it always lists 0, 0, right? 0, 0, 0, 0, 0, right? Because this second decimal place is listed up here at the top. I'm going at this like you've already watched the videos. I'm assuming you have. If you have not, expect to be lost today. Make sure you watch the videos, and then you're going to want to go back and watch this video again, okay? So there's your area to the left of 0. To the left of 0, 0, 0 is half the curve. To the right of 0, 0, 0 is also half the curve, but nothing gives us area to the right. You just have to know that one. Half of the curve is always going to be 0.5. Did I say that right? Yeah, half of the curve is always going to be 0.5, area of 0.5. The entire curve is an area of 1. It includes every probability, 100% or 1, okay? So that's how the standard normal curve looks. Now our data is not necessarily lined up with that. So what we have to do is we have to kind of, you know those old transparency overlays where they drew a picture and then they did another one on clear plastic and they put it on top of it? Well, that's what we're doing. We're mapping our data on top of the standard normal curve so that we can read through it and we can read the probabilities on the standard normal and we can say, okay, those are our probabilities for our data sets. So we're going to be mapping our data on top of a standard normal curve so that we can tell probabilities. So basic thing that I need you to get is z-table only gives you area to the left. Area to the left represents, or the area under the curve represents the probability that something is going to happen. So when you got the area, you got the probability. In this chapter, if they ask you for probability, it's a z-table problem, okay? Not to be confused with what it's going to be later on because we'll add another table to it. This table, this data we're dealing with today is all going to be normally distributed data, and all we're going to deal with in Chapter 6 is population data, okay? Those things are important to keep in mind because those things change when we hit Chapter 7, all right? And they change even more in 8 and 9. All right, so let's take a problem and answer just some basic questions that I thought needed clarification. I think you need to understand them, so I want to stress this. The probability that z is a single value, the probability that you're going to say z is equal to any number is always going to be 0. Now listen what I didn't say. I didn't say the probability that z is going to be greater than a number, less than a number, or greater than or equal, or less than or equal. The probability that z is equal to a single number is always 0. And the reason I know this is because if I were to say to you, I want you to guess a number between 1 and 600,000 million. That's probably not even a number. Let's just go with 600 million. Between 1 and 600 million, guess the number that I'm thinking. What are the odds that you're going to get it right? 1 over 600 million. Practically nothing, right? You don't have a chance, do you? I mean, really. Think about an infinite number of numbers. I'm asking you to guess a number between, infinity that I'm guessing. Any number goes into play. Fractions, decimals, anything. What are your chances of getting it right? 1 over infinity, right? That's 0. The chances in a continuous variable like this, where every possibility is out there, decimals, fractions, smallest we can break down to, chances of it being equal to any one number is always going to be 0. So we're not dealing with the probability of something being equal to something. We're dealing with the probability of it being in a range, less than, greater than, in between two numbers. And we do include less than or equal, greater than or equal, because equal doesn't change anything. Simply the fact that I add an equal sign to greater than, equal doesn't change anything, because probability of being being equal is always going to be 0, so it didn't add a probability to it. Do you understand? Sort of? Listen to the video if you didn't get what I just said, okay? So the probability that z is going to assume a single value is always going to be 0. And the probability, guys, that, now this one is z is less than or equal to a, or z is less than a. Well, those are going to be the same thing, because that equal sign under there does not change the probability at all, okay? Wrap your head around that. That's just something that confuses a lot of people. All right, so now we want to talk about the area, which is going to be the probability, as we know. The area under the standard normal curve to the right of a z-score. Well, I just told you z only gives you area to the left, didn't I? Am I recording this? Good. I just told you z only gives you area to the left. So how in the world am I going to find area to the right of a certain z-score? Well, what I'm going to do is I'm going to say, this is my z-table, and I'm always going to start out labeling it just like that. Before you do anything, do that, okay? Because it identifies this as being the z-table, and the mean of a z-table is always 0. Got it? Now, we want z is equal to 1.06. Well, which side is it on, right or left? It's going to be over here. Now listen, most data falls within 3 standard deviations of the mean. Z-scores are standard deviations from the mean. So if I said if I divided this half of the curve into 3 pieces, I'd have 1, 2, 3, right? Sort of like, that gives you an idea of where 1.06 would be. Not that it matters, really, but it helps you sometimes to be kind of accurate. So I'm going to put it right there. And I'm going to say this is my z of 1.06. And what am I interested in? Well, they told me area to the right. That's this area. That's that area. So I've got it shaded. That's what I need. How big is that area? But z doesn't give me that area. I'm going to go up here and show you what z gives me. It gives me area to the left, always. So you can always draw that arrow to the left, right? So area to the left, I can look it up. It's on the positive side of my z table. You should be doing this with me. Positive side of my z table, 1.06. I go to that table and I go 1.0 is right here, isn't it? And then I have to go over to the next decimal place, which is a 6, and I go down until I see 1.06. And you should be finding 0.8554. Got it? Make sure you can. There's 0.8554, okay? So this area is over 85% of the table. Can you read it like that? Sometimes it makes sense to move that decimal and say, okay, 85%, yep, that's over half of the curve, isn't it? Half the curve would be, okay, so what is the rest of the curve equal to? Well, the whole curve is equal to 1. So if I subtract that left side, I'm going to get the right side. So I go 1 minus 0.8554, and I get 0.1446. So that's the area to the right. How do you find area to the right? Well, you find area to the left and subtract it from 1. Okay? Always. There's a shortcut, but I'm not going to confuse you with it right now. Okay, are we good with area to the right? Okay, let's look at between two z-scores. Between two z-scores, they want the area between a z of 2.32 and 2.33. Well, they're both positive. I'm going to find 0. I'm going to label this as the z table. And I'm going to find 2.32. Well, my basic thing here is give myself enough room to write the numbers, because I don't really know how big that area is between the two. But I gave myself enough space to write them, and they're on the correct side of the curve. And then I'm going to come up here and say, okay, what can I look up? Well, I can look up this area, and I can look up this area, right? That's all I can look up, area to the left. So I go to the z table and I go 2.32. Okay, positive side again, 2.3. And over here, you're going to have to trust me because I can't get this on one page here. Maybe I can. No, I can't. So 2.3, and I go over to the third column, which is 02. 2.32 would be 0.9898. You should be finding this. Make sure you can find this, okay? So I got 0.9898. Which was that? This was this one, right? Now I've got to go to 2.33. 2.33 is the next one over, 0.9901. Now, how would you find the area between those two? Yeah, you take the bigger one. Well, the bigger one's 0.9901, and you subtract the smaller one, 0.9898, and you get that big. It's not a big area, is it? I mean, if I was looking at this as a percentage, I would be saying this thing is 0.03%, right? It's not 3%, it's 0.03%. We can only move that decimal 2 places if we're, so that's small, isn't it? Tiny little area. I mean, I know my picture doesn't show that, but that's okay. Are you good so far? How do you find the area to the right? Well, you find the area to the left, subtract it from 1. How do you find the area between two z-scores? Look up both of them, subtract the smaller area from the bigger area. It gives you area between. Always. This is always, okay? How would I find the area to the left? Well, you just look it up. That's not hard, is it? If they just ask me the area to the left, all I've got to do is look it up. So now let's talk about the next thing that they could ask us. They might ask us about standard deviations from the mean, not z-scores at all. And they might say something like, how big is the area within 2 standard deviations of the mean? Well, Standard deviations from the mean are z-scores. That's what z-scores are, aren't they? So if I say within 2 standard deviations of the mean, I'm saying within 2 z-scores. Well, I come over here and I go, okay, 2 z-scores from the mean would be a -2. 2 z-scores from the mean over here would be a +2. I want this area between them, don't I? Well, that's easy. I look them both up, and I subtract the smaller one from the bigger one. Well, how do I find 2 standard deviations from the mean? This one is a -2. I go to the negative side of my z-table, and I look for -2. Well, -2.0, and the first column is 0, so that's it, right? -2.00 is -2, and I get 0.0228. Yeah, that's this area. And then I go to a +2. And 2.00 on the positive side is 0.9772, isn't it? So then you take them and subtract them. And you come up with, I'm doing the math for you, but I know you're capable of calculator punching in, subtraction. And you come up with 0.9544. Now that sort of plays into what we know about Chebyshev and the empirical rule, doesn't it? Within 2 standard deviations of the mean, how much? 95%, right? Isn't that what that says in the empirical rule? And this is a standard normal curve, so it is perfectly distributed. Okay? Let's take it a little step further. Let's talk now about data values. We've been talking about z-scores. Those are standard deviations. Let's talk about data values here. Let's look at this problem. It says x. Whenever they say x, they're talking about actual data, okay? Now, this complicates our z-table thing a little bit because z-tables only talk about standard deviations. So we got to figure a way to map that back to the standard normal curve. So we're going to layer it, guys. We're going to layer this on top. Whenever they say x values and you're talking about probability, those are the things. X is in it, wants us to find probability. I know I'm going to take this z-table, and I know I'm going to map on top of it. I'm just writing it underneath it, the x values, okay? So the mean of the z-table is 0, always. But the mean of this data that they gave me is 1650. Okay? Now I've got it like laid on top of it. So I'm going to look through it. I'm going to look through the data to get to the z-table. And sometimes I look through the z-table to get to the data. Sometimes I have to do both. What did they tell me? They said a mean of 650, standard deviation of 170, population data. Look at the symbols, right? And they want to say, what's the probability? Go to 4 decimal places. And we want the probability that x, our data value, is going to be greater than 1543. Well, now look, if they had put greater than or equal to, it would not have changed anything. Remember, equal doesn't add any probability to anything, does it? So we don't care. We simply say, where is x going to be 1543? That's going to be my cutoff. Well, 1543 is smaller than my mean, isn't it? So I'm going to come over here and say, this is what they want. Here's my 1543 that they gave me. Did they give me a z? Nope. So put a block to show that you're going to have to calculate it, okay? You got to find it. But they did say they want everything greater than. Well, that's all of this. It's an area to the right problem, right? Area to the right. So what am I going to do? I'm going to find this, and I'm going to look up the area to the left, and then I'm going to calculate the area to the right by saying 1 minus whatever. I know what I'm going to do. I say, how do I get to that z-score, though? They didn't tell me the z-score. They told me the data value. But I have a formula, and my formula says z is equal to x minus the mean divided by the standard deviations. You don't have 2 formulas in this chapter. That's one of them. So I'm going to say, okay, I know that z-score is going to be the x value. Okay, the x value that they told me I'm interested in, I already wrote it in. It's 1543. Minus the mean, well, I already put it on my chart, so that makes it easy. And I'm going to divide by the standard deviation that they also gave me. And I'm going to come up with a z-score. Now look at your chart. Is that z-score going to be positive or negative? Negative, better be negative. And when we do this subtraction, we see that we have a negative number in the numerator. It's going to be negative. That's a good check for us. And it comes up to negative 0.63. If it goes past 2 decimal places, round it to 2. That's the z-score I want. It's now become a simple z-table problem, hasn't it? I look up that negative 0.63, negative 0.6, and trust me on this one, that's the column 0.03 column, right? And it is 0.2643. I think I got that right. This area is 0.2643. That's not the area I want. I want the rest of the curve, which I have to take 2 points. Okay, I have to subtract this from 1. And I get 0.7357. That's the probability. What's the probability? That it's going to be greater than 1543, and they say round to 4 decimal places. It's going to be 0.7357. In other words, 73.57%, right? Don't put it in percents unless they ask you to, but most of us don't think in decimals, we think in percentages. So that kind of gives you an idea. Look, it's over half the curve, isn't it? Okay, your picture should match up. You should double check yourself just like I'm doing right now. All right, number 6, student loan debt is a growing problem. According to Experian, each borrower owes an average of $31,760 unless you go to IRSC, which average debt is almost nothing, okay? Just saying. The standard deviation of the amounts all student borrowers owe is $1,200. Determine the probability a randomly selected student owes between these two numbers and round it to 4 decimal places. So read through a problem. Everything from now on out, guys, is word problems. For the rest of our time together, it's all word problems. Your job is to read through it one time, then go through it a second time and find important things. In other words, I go through it the second time and I say, average of 760, that's the mean. Standard deviation of 1,200. And they want us to go between these two x values. If they hadn't written the probability statement for me, I would write it myself. X has got to be between those numbers. It's the same thing as the probability that z is going to be between a couple of numbers, okay? What are the z numbers? Well, we have to figure those out. The first thing we do, though, is let's draw it on top of this standard normal curve. So there's my base layer. And I've got x values with a mean of 31,760. And I want to go between 28, 626, and 33. So I'm going to go one on each side, right? Hardest part sometimes is giving yourself room to write the numbers when they're big like this. I don't know that z-score. And I'm going to go over here and say it's between, here's another one. They want it to be, these are the numbers I have to pick it between, 898, right? The area I'm interested in is the area between those two. If I find that area, I have the probability, and listen to the way it's worded, that a randomly selected student will have a debt between those two numbers. So I need 2 z-scores. I'm going to find them, areas to the left, and I'm going to subtract the smaller from the bigger one, and I'll have the area between. But I first have to find the z-scores. There's 2 of them. So I'm going to do 2 calculations. I'll call this one z1. I'm going to say that's equal to the x value of 28,626, the data value, minus the mean of 31,760, and I'll divide it by my standard deviation up here, 1,200. And what I get when I do that is a negative z-score of negative 2.61. It should have been negative. It's on the negative side of my curve, right? The second z-score, well, I'm going to deal with this data value, this x value. So it's going to be 33,898 minus the mean, always the number in the middle, right? Divided by the standard deviation. And this time I get a positive z, 1.78. Well, it should have been positive. It's on the right side, isn't it? And now I go to my table. I'll look up the negative 2.61, and here it is, 0.0045. That's this area. And I'll go to the positive side and look up 1.78. And it is over here. It's 0.9625, isn't it? Sorry. And I subtract those to get the area in between. The area in between is 0.9580. That's my probability, isn't it? So there's a pretty good chance. Over 95%, almost 96% of students will have a debt between those two numbers. And now is where our probability makes sense, because we're actually able to answer real-life questions with this standard normal table, which before all we were talking about was abstract between so many standard deviations of the mean. Have you ever read an article that said to you something like 95%, over 95% of all students get out of college with a student debt between negative 2.61 and positive 1.78 standard deviations of the mean? Who knows what that is, right? So we don't talk in standard deviations of the mean. We just use standard deviations to interpret the actual data. And that's why I'm saying we take that standard normal table and we lay our data on top of it, and we get the probabilities by looking through the data, okay? Think transparencies. Any of you ever remember those transparencies? Remember how they used to have a big machine? No, you don't remember that. Never mind. Okay. Okay, next page. I'm going to bring one in one day because it makes sense to interpret it that way. All right, let's talk about freestyle times of a college swim team, which are normally distributed. And when you see the words normally distributed, that means we can use the z-table, because the z-table is normally distributed. You can't map something on top of it that's not normally distributed, okay? So normally distributed has a mean. Here's our mean. I'm going to go ahead and pull it out of 24.42. I would normally read it once first. And a standard deviation of 3.14. The reason I say read it first is because sometimes they're going to give you extra stuff. They'll give you numbers in a problem that you don't need. If you read it one time and try to pick all the numbers out, you're going to pick out some numbers that are unnecessary. Okay, so next, determine the probability a randomly selected swimmer has a 50-yard freestyle time of 17.06 or less. Now, you see this number? Some of you want to use that. It isn't a number to be used in the problem. It's simply telling us what type of race they run, right? So the 50 yards doesn't mean anything to us. It's their freestyle time race, okay? Could have been 100, could have been, it could have been an IM, it could have been anything. Okay, so the time we're interested in here is 17.06 or less. The probability statement is written for us. We're going to draw the curve. Because it's probability, and it's a standard normal distribution, we use the z-table. And then on top of it, we're going to say, well, what's the mean of this thing? Well, it's going to be 24.42. Okay, and then we want to go freestyle time. We're interested in 17.06. That's down here, right? And we want less than that, don't we? 17.06 or less. So, same thing. All we got to do is find that z-score, and then when we look it up, we have what we want. No need to subtract it from 1 or subtract it from anything. It is the answer. First, I have to calculate it, though. Z is equal to the data value I'm interested in minus the mean divided by the standard deviation, and that's coming out to be a negative 2.34. I go to the z-table. Negative 2.3 is right here. 4 is right there. 0.0096 is what the area is. And that's my probability. 0.96%. Not many of them swim that fast, do they? Well, you wouldn't expect them to because that's the average, isn't it? So going less than, below average, there aren't too many swimmers that can do that. Does that make sense? Always try to interpret the problem so that you see if you're on track or not. It'll tell you if you're not. All right. Now we're going to switch gears. Now we're going to have to say, okay, we don't know the z-score, but we know the area. Now before this, we've been calculating the area, haven't we? We've been finding the x, we've been finding the z, okay, what if they gave us something totally different? What if they said the area to the left of z is that? Well, draw this, okay? We're not dealing with x values here. We're just dealing with the z table, so let's just put the z table up. And we're going to say area to the left, is that bigger than half or not? Somebody be brave. Is 0.9971 greater than half of the curve? Yeah, don't be afraid. Yeah, 0.5 is half. This is a lot bigger. So where is this z-score going to be? Left or right? Yeah, it's going to be over here somewhere. Because what they just told us is that this area is 0.9971. They didn't tell us the z-score. If you will get in a habit of doing what I'm doing, always represent the area with these arrows, always put a block around the information you don't know, it'll help you, especially when we get into calculating probabilities. Okay, so go back to what you know. My algebra, that just flashed back to 10th grade for me. My algebra teacher used to say that all the time. Go back to what you know. Look at what you know, because you only have what you know. Well, what I know is the area is 0.9971. I know I'm dealing with a z-table. Well, look at your z-table. Where do I find an area? Now remember, area in the z-table is these big 4-digit decimal places, right? It's the inside. It's not the z-scores. That's what I need to know. What I know is 0.9971. Which side of the table am I going to look on? Positive or negative? Positive, yeah. Positive. And now I go looking for this. Now I will grant you this is probably the hardest searching I have to do. And so it's going to be the hardest searching you have to do, because you have to really pay attention to the decimals. And sometimes it's 0.0003, and I have a tendency to look for 0.003, which is not the same thing at all. Be careful, okay? 0.99, well, I'm looking at it. 9 5s are up here, 9 8s are down here. I'm going down till I get to, okay, I'm looking, I see some 9 9s. 9971, okay, well, this is 6, and that's 6 6, and that's, I'm going in the right direction. And I happen to find it. You won't always find it, because, look, every number is not necessarily represented here, but you get as close as you can, okay? Actually, this z-table does a much better job than our last one. But anyway, 2.76 is what I'm finding. Do you see it? I found the exact area. I go out here and I go 2.7, and then I go up to the top for the next digit, and it's 6. That z-score is 2.76. So that was all it asked me, wasn't it? What's the z-score when the area to the left is 0.9971? All right, here's another question. Find the value of z when the area to the right is 0.2514. Well, once again, start off the same way. There's my standard normal curve. Area to the right. Ask yourself, is that bigger than half of the curve or less than half of the curve? Less than. Area to the right is over here, and is it ever going to get as far as the 0? Nope, it's not. In other words, I want to draw a line so that the area to the right is smaller than half the curve. That means I have a positive z-score. That's the reason, guys, that we draw these curves, is because otherwise you just have to kind of know what you're doing, really know what you're doing. And most of us haven't reached that level yet. So what is the other side going to be equal? Because z is only going to allow me to look up area to the left, right? It's not going to let me look up area to the right. What's the area to the left? How would I find it? Somebody? Yeah, Yeah, you would subtract it from 1. You're going to go 1 minus 0.2514. That gives me the area to the right, which is necessarily bigger, isn't it? I didn't do that. I did the shortcut, which I'm about to show you, but do it. Subtract. Did we get 0.7486? That's the area you're looking for. Which side of the table? Well, the z-score is on the positive side. Go to the positive side. You knew it was going to be. That's a bigger than half area, right? It's greater than 0.5. Do you see 0.7486? Anybody find it? Yep, 0.6, right here, right? It's hard, the angle I'm looking at is really weird. 0.67, is that what we got? Okay, so this z-score is 0.67, okay? So you use the same techniques, you just had to answer different questions about it, didn't you? Okay, I want to show you something. This area to the right can be looked up on the opposite side of the table, and you wouldn't have to subtract from 1 to get it. You could just look it up on the other side of the table. You could look up 0.2514. Okay, well, let's do that. Go to the negative side of the table and look up 0.2514. Here it is. It's negative 0.67. Look, it's the opposite, isn't it? That's the shortcut. When you need an area to the right, you can look it up over here and just take the positive z-score. Don't use it if it confuses you, okay? Okay, next one. We want the z-value, the area between the area between 0 and z is 0.4922. Well, here's 0, right? And the z they're interested in has an area between it of 0.4922, and it told us z is positive. It had to tell us that because that would have made it either way, could have been half, less than half the curve, right? So I'm going to go over here and say it's over here somewhere. This area right here is 0.4922. That's not the area I look up, though. The z-score is associated with this area from there all the way to the left. How big is that area? Do you know? Think about it. This is that part of it, and the rest of the curve is worth how much? 0.5. So if I want this whole area, I just have to add them together, don't I? Doesn't that make sense? The reason we draw the pictures is because every problem is different. I'm trying to give you a nice selection so that you'll see the differences, but every problem potentially is different, okay? Okay, so now I'm going to say I need to look up 0.9922, and you know how to do this. You go to the positive side, I go to 0.999999s. Oh, there it is. 2.42 is what it looks like. Whoops. So I got 2.42. And I've answered that question. All right, now, why did we have to learn to do this anyway? Because now they're going to ask us questions that have to do with probability, which has to do with area, which they may give us the area they're interested in, and then we have to figure out the z-scores, and then we may even have to figure out the data values from that, okay? So we may have lots of unknowns here. So let's take this question. It says two values of z. Determine the two values of z, such as the middle 80% lie between those two z values. Okay, middle 80%. Ooh. So here it is. Now I want the middle 80%, okay? I'm going to center it on 0. So I'm going to go out here and say, okay, one of my z-scores is here, and one of my z-scores is here. And this part right here is 0.8. That's 80%, right? So how much is this? I mean, basically we're saying split it. This is 0.4 and this is 0.4, isn't it? Right? So if you were doing this, I also know that this is 0.5, don't I? Right? I mean, I'm just putting down everything I know, hoping eventually some of it makes sense to me. So now I can get this z-score. How would I get this big long area? Well, it's equal to this 0.5 plus that 0.4, isn't it? That one is 0.9, right? I got one. I know how to look that one up. That's all I need. Guys, that's all I need. This table is mirror images of each other, okay? When I find this score, that score is going to be the negative version of it because they're exactly the same, both sides of the curve. All I have to do is go to the positive side and look up 0.9. Okay, I'm looking up the area, so I want 0.9000, right? I'm not going to find it, but I'm going to get as close as I can to 0.9. Did I do this one right? 0.9. Yeah, didn't do this one right. Okay, so I want 0.90, 0.9, 0.89, 0.909, 0.9082. Keep going down until I get to as close to 0.9 as I can get. Do you see it? As close to 0.9 as I can get. It's going to be between these two, but I'm going to go with this one as being closer. Wouldn't it be closer to 0.9? So I'm going to say 1.28. That's going to be this one. What's the other z-score? Negative 1.28. Okay? You could have found the other one. You could have found the other one by saying this is 0.4, therefore this part right here, you know, is going to be 0.1, isn't it? Maybe you could have looked that one up. So what are we between? A negative 1.28 and a positive 1.28. Okay. X is normally distributed continuous random variable. It has a mean of 75 and a standard deviation of 2.5. Can you see this? Okay. Mean is equal to 75. Standard deviation is equal to 2.5. We want the value of X so that the area to the left of X is 12.92. Well, we know we're dealing with the Z table, so we do that one first. We know we're dealing with X values on top of it, so we're going to put the X values and we're going to map it on top. There's our second layer, okay? They gave us the area to the left of X as being smaller than half, right? Area to the left is less than half. It's got to be over here on the negative side. So this area to the left, I don't know where it is, but I can sort of estimate 0.1292. Okay. Did they tell me the z-score? Nope. Did they tell me the X value? Nope. Look, I know nothing, right? The only thing I know is the area to the left of this particular X value z-score is going to be 0.1292. But I can find the z-score, can't I? If you know the area, you can find the z-score. I know the area to the left. I go to my z-table and I look up the score. It's going to be on the negative side. 0.1292, where is it? Oh, it happens to be there. It's going to be 1.13. Do you see it? Okay, so I got this score, negative 1. What did I say it was? 13. Now I have a calculation. I have the second formula that you have in this chapter. You only have two. How do you calculate X values when you know the mean, the standard deviation, and the z-score? Well, the calculation is X is equal to the mean plus the the z-score times the standard deviation. That's your calculation. It's not hard. So X is going to equal to that mean, which is 75. And we're going to say plus, well, I've got a negative z-score, negative 1.13, times my standard deviation of 2.5. Now look, do this carefully because the negative is in there, right? And when you do it in your calculator, I'm just going to do this for you once. It's going to be 75, and I would say, you can say plus and negative, or you can say minus and then whatever you want to do, but I'm going to say plus because I did it that way, okay? And then I say negative 1.13, and then I say times 2.5. It should do this correctly, and I get 72.175, okay? You don't really have to use parentheses in these, but you can. If you did, you would put the multiplication in parentheses. Just make sure you know that which one is your negative. It's not the same as your minus sign, right? So I've got x is equal to 72.175. It said go to 2 decimal places, 72.18, right? That's my answer, isn't it? What is x equal to? 72.18. So if I don't have z, and I don't have x, but I have the area, I can take the area and I can get to z. I can use z to get to x. I can figure anything out from anything they give me. Are you good so far? Are you confused? You okay? All right. Last page. Lots of words. A technology company manufactures smartphones would like to set a warranty period. And this warranty period says a company is going to replace any smartphone that fails within that period. So research has shown an average lifespan of 55 months with a standard deviation of 4 months. Now, this is normally distributed. These are all things it has to tell us for us to use the z-table, okay? Normally distributed is good. We can use the z-table for probability. This company's management has decided it wants to replace no more than 18% of the smartphones it sells. Determine the length of the warranty period for these smartphones so that no more than 18% should fall within the warranty period, okay? That's kind of confusing, but what you have to do is sort of draw your picture like this. All right, now I know that I'm going to be using the z-table. And I know I also have data values with a mean of, what was my mean of that one? Average lifespan was 55 months, right? I'm going to write it down out here, outside the problem. And what was the standard deviation was 4, right? Okay, so I've got a mean of 55, I've got a standard deviation of 4, and they want to only replace 18%. I mean, you know, they don't want to replace more than 18%, less than, 18% or less than, right? So I'm going to come over here and say, well, that's going to be the area, 0.18, isn't it? That's going to be my area that I'm looking for. So I'm going to say area of 0.18 or less would look like that, wouldn't it? Now from that, can you tell me the z-score? And then once you have the z-score, can you get the data value? And when you have that, you have how many months are associated with that 18%, don't you? Not really. So we're going to look up the z-score. We're going to go, where's 0.18? Well, it's on the negative side, 0.18. I think I'm really close to, I guess I'll go right here, 0.1814. It's close as I can get, isn't it? That's going to be 0.91, negative 0.91. Okay, and I'm going to calculate my x value from that. I'm going to say I got an x value of the mean, which was 55, plus the z-score of a negative 0.91 times the standard deviation of 4, which is going to come out to be 51.36. Okay. So far I'm pretty good because look, my data value is less than my mean. I mean, things that trip you up, things you can check. Data value is less than mean. I know that I want less than that, that particular area, right? So I'm good with this being 51.36 months. So what I'm saying is, what should the warranty period be? Well, let's round it to whole numbers. That's what it told us to do, round to the nearest whole number. How many months should I make the warranty for? I would go with 51 months. If I go with more than 51 months, I'm going to have greater than 18% failure, right? Greater than 18% that I have to replace. Okay, so now it asks another question. It says, somebody messed up. And instead of printing the 51 months, they printed 54 months as their warranty period. So now the company wants to know, what percentage are we going to have to replace, okay? So we're going to go and say, okay, they messed up. They gave an X value of 54. That's the Z-score I need, right? And that is the percentage that they will now have to replace, isn't it? Well, if I know I have this X of 54, can I calculate the Z? It's equal to the 54 minus 55, which is the mean, divided by the standard deviation. What was it? 4? It's going to give me a negative Z of 0.25. Does that fit with my curve that I've drawn? Yep, looks right, doesn't it? What percentage will they have to replace this time? Well, what's the area, right? What's the probability that they're going to fail? I go to negative 0.25, and I'm over here at, well, here it is, right? Can you see it? 0.4013. True? Okay. 0.4013. Wow, they're going to have to replace over 40%. They didn't want to replace but 18%. But because somebody made a mistake, and instead of printing the 51 as the warranty, they put 54 down there, all of a sudden it's costing the company a lot of money, and somebody lost their job, right? Probably. Are you good with that? That's a hard problem. That's a really complicated problem. It's the reason I'm going over it. I got another hard one for you in front of this one and behind this one. The last one we hit today, don't go to sleep on me, okay? This one says that the New York City Marathon is highly selective, and one way to get into the race is to qualify based on time from another marathon that you have run. Do you guys run marathons? I mean, I'm shocked that the average time of all marathons that people run is 180 minutes. It's 23-something miles, isn't it? In 180 minutes. Seems impossible. Anyway, the New York City Marathon organizers decided they would limit admission to the top 8%. They only want to let the top 8% of all times get into marathon runners. The mean competition for all marathon runners, in other words, the completion time, the mean is 180. I'm going to write it down. 180 minutes is the mean. Standard deviation, 23. So they want to know, what should they set as the qualifying time so that they only take the top 8%? Now we have to kind of reverse our thinking on this one. Top 8% of all marathon runners have lower times, don't they? Oh, that makes it different, doesn't it? So when you see that, you say the top 8% have the lowest times. You have to know what you're talking about, don't you? You have to think about it. They're going to have the lowest 8% of the times, aren't they? That's the way it works. It's like golf, you know, the higher your score, the worse you are, right? The more time it takes you to run, the worse you are. Okay, so we're not going to be able to compare this the way, we're going to have to kind of reverse it the way we think about it. We know we're using the Z-table. We know we have data values, and we know we have a mean of 180. Well, there, I got that right. I got the curves mapped. Now, I want only the top 8%. I know they have to have the lowest 8% of the times, don't they? So I'm going to say 8%. It's going to be over here somewhere, isn't it? So it's going to be 0.08, 8%. Think about it, right? Okay. Do I know the Z-score? Nope. Do I know the X value? Well, that's eventually what I want to know. I can get to the Z-score. I can look up 0.08 over there on my Z-table, can't I? I get as close as I can get to it. I'm going to go with this one. It's pretty close, 0.0808. So I'll say 1.40, negative 1.40. Now I can calculate that x value. I say I take the mean, and I add that negative the z-score times the standard deviation, and I come up with a 147.8. Okay, so what is the qualifying time set to? It told me to go to 1 decimal place. I'm at 1 decimal place. What you have to have done to run in the New York City Marathon is you have to have run a marathon, any marathon that was recorded and timed and all that stuff, at 147.8 minutes or less, right? And that will give him only the top 8% of all runners. The top 8% would have the lowest times, wouldn't it? The lowest 8% of the times. That one seems backwards to us until we remember that things like running times and golf scores, the lower the score, the better you are, okay? So you really have to think through some of these problems, what they're asking you. Are you good? Kind of? I know I hit you with a lot today. Was there something else I needed to tell you? I can't remember. I don't think so. This is the class I kept really late one day, so I'm going to let you go. I'm letting you go early, right? I don't have a clue what time class is in these days. All right. Do the work on this one so that you're ready for Chapter 7 next week, because we do Chapter 7 next week, and we do the test the week after. And let me know if you need help. I'm in office hours Sunday evenings from 5:30 to 8, all by myself, sitting there buying things on Amazon, okay? So show up.